There we go. All right, good morning, everyone. How are you all doing? Good, good. Cool. All right, so we are about to finish the last of the new material before the next exam. So we will finish the material probably today. If we don't, then we'll finish it on Monday, but we'll probably finish it today. There is no quiz this weekend, so yay. Do make sure that next week you do the pre-exam 2 survey, and so then your exam is in a week and a half. So on Monday, what we're going to do is a synthesis. We're going to try to incorporate everything that we've learned so far into doing complex exam level problems. So it'll just be a lot of practice, essentially, for the synthesis. And then, depending on how we're feeling, we might spill it over into Wednesday. And then we'll theoretically start chapter 12, chapter 12 being our alkene additions. And then I have it built in that we're doing a review session on Monday. So next week might get a little awkward, is what I'm just trying to say. That we'll have it that way. But make sure you're doing the homework, and yeah. We'll kind of play next week by ear to see how we're feeling and how prepared we are for the exam. It's kind of the gist of what I'm trying to get at. All right. Does anyone have any questions before we get started? Yes. There was the homework that was due this past weekend, yeah. Oh, this coming weekend? No. No, there's no homework due this weekend. No. So I did that in case we don't finish chapter 9, then it'll be due the next weekend, just in case. So you should be able to do, actually you should be able to do all of it, but you can definitely do at least half of it confidently. So I'd recommend starting it. That we don't have to worry about it right before the exam, but yes, there's no homework due this weekend. Any other questions? Cool. Let's do chapter 9. All right, so one thing I will apologize, I forgot to fix these before today. So one, we're gonna have a little bit of blank spaces on the first page. So we'll have a little bit more writing on the first page, and then there'll be less writing as we go. But yeah, we're gonna have some errors to correct as we're writing. So I'll point them out, just be aware of the fact that like some of the formatting is really messed up and I just forgot to fix everything before today. Okay, so chapter 9 is more review. It's more substitution reactions, but it's just looking at ethers specifically. So having our ether groups, where you have the single bond between a carbon and oxygen and then single bond to another carbon on the other side. We're looking at those ether functional groups that are also ubiquitous in natural products. They're really common motifs. So because they are also important functional groups, that's why we're calling them out as well. And then especially when we talk about cyclic ethers in a ring, they're gonna have some special unique reactivity. That's what we're gonna wanna focus on. So thinking about our alkoxides, those alkoxides are going to be really strong bases. We know that, it's O-. Alkoxide is RO-, right? So that O- is gonna be a strong base. It was also a strong nucleophile as long as it wasn't the tert-butyl. But the way that we actually make them is one of two ways. Either, actually there are a couple different ways, but the main ways are doing a metal insertion. So it's gonna be a single electron transfer using either sodium metal or potassium metal. So it's just straight up metal. And essentially what it's going to do is just bump out that hydrogen and it's gonna kick it out. So you lose hydrogen gas and then you just get that O-. So the sodium metal, you just mix it and then you see the bubbling come out and that makes the hydrogen gas. The more common way, that's more on like an industrial scale that you would do that. The more common way if you're in a lab is just do an acid-base reaction. So you would just do a normal, add a stronger base to make that base. So if you add sodium hydride or potassium hydride, that's going to do that acid-base reaction where it just deprotonates, gives the electrons to the oxygen, and then again, it's going to be irreversible. It's not a reversible acid base. This is a true forward arrow because you're making hydrogen gas. So it irreversibly makes that alkoxide. So that's how we make those O minuses. Another reaction that we can do with our alcohols is to make an ester. So this is a really common lab. Are we okay? Are there questions? Bless you. Okay. It's a really common lab because it usually works really well, doing the Fischer esterification. So it's where you have that carboxylic acid, an alcohol, and a strong acid. And that will make our ester and kick out water. So what we're doing is just a substitution where that OR is just swapping out that OH. This is another Orgo-2 concept that will come in later, but I'm just pointing out the fact that this just is something else you can do with an alcohol, that it's just, this reaction happens pretty readily, it happens very well. So that's another mechanism you don't need to know because it's an Orgo-2 mechanism. For our haloalkanes, if you want to make a haloalkane from an alcohol, let's talk about that. All right, so let's say you have OH and you want to make that Br. You want to do that substitution. How would you go about doing that? Yeah, so we could protonate the alcohol. That would make it a leaving group. So what kind of reagent would you want to add? Yeah, so I'd want to add an acid. So what acid do you think you would pick? Yeah, so which strong acid is going to give you the element that you need? Yeah, HBr. So I really love that, one, you participated, but two, that like train of thought, that's the kind of series of questions you want to be asking yourself when you're doing these problems of how do I make it happen? Okay, well, I need to turn the alcohol into a good leaving group. Okay, how do I make it a good leaving group? Okay, I could protonate it. Okay, how do I protonate it? Strong acid. Okay, so which strong acid? All right, well, I have all these options. Which one might actually get me to the desired product I want? Which one gives me the elements I need? HBr. So that's absolutely correct. HBr will work to get us that product. So why couldn't we add NABr? So we kind of hinted at it. Yeah, so essentially we need that alcohol to be a better leaving group. So the question kind of becomes, why is the alcohol a bad leaving group? It's not stable on its own. It's going to be reactive. We're making a strong base. We're making O-, right? We said O- wants to react. So you're not going to be able to do this transformation directly. It will not see this because it's going to go backwards. The favored direction is to make the alcohol. So if any of it does go forward and you get the hydroxide, it's going to immediately go right back, where it's going to immediately just go back to the alcohol. So you can add strong acid, and that will work, but we can't add our NABr. You can't add the Br- directly as the salt. That one doesn't work. So if we want our reaction to occur, and let's say we want SN2, and I want it to be SN2, but maybe I have like a secondary, and I run the risk of having a rearrangement. and I want to avoid rearrangements, I'm going to need a different reagent because I just said I can't use sodium bromide, which is the one that I would have done to try to do SN2. Hydrobromic acid has the issue of you could do rearrangements. I mean, you wouldn't here because it's primary, so we didn't have to worry about that there. But there are other substrates where we might risk having a potential rearrangement. So that's where these reagents come into play. So thionyl chloride and phosphorus halides, these are our really useful reagents that are going to let us turn our alcohols into our halogens via SN2 reactions without making hydroxide as byproduct. So it's basically, we're going to change our byproduct to make sure that we can do this reaction, so that we can favor this side. So it's SN2 without making the hydroxide as the byproduct, so it actually goes forward, is going to be the benefit. That's why we have these reagents. So thionyl chloride is Cl2SO, so it is this reagent. So it's where you have the sulfur-oxygen double bond and then chlorine on either side. If I have that plus my alcohol, how do you think these reagents will react? Do you think the thionyl chloride is going to be the nucleophile or the electrophile? Electrophile, why? Yeah. Yeah, it is. So it's because Cl is a good leaving group. So remember, when you find that leaving group, that's on the electrophile. So we see that that is a good leaving group. So then that alcohol also has lone pairs, so it can be a nucleophile. So it's absolutely going to be that. So that's my nucleophile. This is my electrophile. So let's make them meet. So if I attack the sulfur so that I can kick out the chlorine, I'm going to do what reaction mechanism did I just do? If my nucleophile is attacking, leaving group is leaving at the same time. SN2. Beautiful. So that thing looks weird, probably. Are there questions? Sorry, there's a lot of conversation. Oh, are you on the phone or listening to some? Can you mute whatever conversation you're having? Thank you. It looks really wonky, but this is essentially a leaving group. So if I made this a hydrogen, like that would look like our oxonium ion, right? That would look like a good leaving group. So it looks weird, but it's absolutely, this is still just a leaving group. So I have a good leaving group. I have a nucleophile. That chloride's going to be able to attack, kick out that oxygen. And what mechanism did I just do? SN2, my nucleophile is attacking at the same time as leaving group is leaving. So thionyl chloride, even though it looks weird, it is just two SN2 reactions. So the driving force, what is actually making this reaction go forward, why this is an improvement, is going to be the byproducts that we make here. So we just made our desired reagent, or desired product, right? We made the haloalkane. But what makes this reagent special is what's going to happen from this reagent afterwards. So the way this breaks down is that this oxygen is going to push electrons in and kick out that other chlorine. So that's just doing an elimination reaction. Woo, come back here. Oops. And I know I told you never use chloride as a base. However, the difference here is I don't have anything else in solution that could be a base. Also, I'm going to make hydrochloric acid gas. So I'm going to produce a product, the gas, that is going to be able to bubble out. So I get hydrochloric acid gas and sulfur dioxide gas. So that's the driving force, is we're doing this like Le Chatelier. So this truly is a straight up forward arrow. This one must be forward. Because we're making that gas, so it must be a forward arrow, and that's our driving force. So we're going to Le Chatelier this forward because we are bubbling out this product. So as we remove that product, it's going to funnel everything, just keep pulling it forward. So it just cycles in, makes the gas bubbles out, and then it comes forward, and it just keeps doing this loop. So that's the benefit of our thionyl chloride, is it is going to make products that bubble out, go away, and we don't have to worry about any other byproducts or any other reactivity. It must occur via SN2. It will not happen via an SN1 reaction. It is SN2 only, which means you cannot have a tertiary alcohol. So this will only work with our primaries and our secondaries because it is SN2. Yes? Yes, that would work. So the alternative being, instead of it being HBr, you do H2SO4 and then NABr. Yes, that would be an alternative that would work. Because you're essentially just having a different strong acid, but still getting the bromide nucleophile. So yeah, that'll absolutely still work. It still has the concern of if it's the secondary, you could still have rearrangements and you still have some other concerns, but that is 100% a valid set of reagents that you could do for that reaction, for that substrate. Yeah, if you wrote that, you would get full credit. Yeah. Yeah, so for this elimination reaction, the oxygen is making this double bond. And so when these electrons come over, it's essentially lengthening this bond so much that it's pushing this chlorine out. So I'm just making a double bond between the oxygen and the sulfur, and then breaking the bond between the sulfur and the chlorine. And again, the reason why we do that is to get specifically to these products. That's why we're trying to do these. Like, those are just reasonable sets of arrows that just get us here, because that's what we want to get to. Cool. Yes? This elimination is actually neither E1 nor E2. This is a different type of elimination. So that's actually a really good question. So our E2, remember that E2 requires that antiperiplanar. Oops. I'll just make a generic base. So it is where you're going across. So you have to have 4 atoms, essentially. So this is only 3. So there's no way for this to be E2, right? even with that like weird E2 alpha elimination that we did with our oxidation, that still had the 4 atoms. It had hydrogen, carbon, oxygen, and then that manganese or chromium leaving group. It still had the 4 elements. Here we're 3, so it can't be E2. And then it also can't be E1 because we're not making a carbocation. So E1 requires the carbocation. So there are actually a lot of different ways we can do eliminations. The 3 main ways are E1, E2, and E1CB. So the E1CB gets introduced usually at the end of Orgo 2. And then this is just, we know it's elimination because I'm going from no double bond to double bond. It doesn't have a special name. It's not common enough for it to be seen or like have a special name. Cool. All right. Any other questions? Okay. All right, then let's do our phosphorus trihalide. So, one other thing to point out, this could have been Br2SO, so you can have the other halogen. Thionyl chloride as opposed to thionyl bromide is more common. So having chlorine as opposed to bromine is just, it's more commercially available, it's easier to access. So that's normally what people will use, but it technically could be the bromine. That would also work, because I just want to point out that like we started talking about bromine and then I started talking about chlorine. It does work either way. And the same thing goes for our phosphorus halides. So that could be PCl3 or PBr3. The phosphorus tribromide is the one that is usually more commercially available. So that's usually the one that people use, is that they're trying to get to the bromine. Again, you can use either one, but if you were in a lab setting, you wouldn't normally, your boss probably wouldn't approve you to buy PCl3. They would tell you to either buy thionyl chloride if you want the chlorine, or if you want the bromine, then you buy phosphorus tribromide, right? So, because we're not in a lab and we don't have to have our expenses approved, you can write whatever you want. You can use whichever halogen you want, but it's really only putting on the chlorine and the bromine. It's not a good way to add iodine. So for this reaction, what's going to be my nucleophile? What's going to be my electrophile? Yeah. Beautiful. The PBr3 is my electrophile. The alcohol is my nucleophile. How did you do that? Exactly right. It's the exact same reason as before. That bromine is a good leaving group. So leaving groups are on the electrophiles. And the alcohol has a lone pair, so it can act as a nucleophile. So we see that matched reactivity to tell us, yes, we're going to have a reaction go forward. So we again are going to do alcohol attacks the phosphorus, and we kick out the bromine, because that is going to kick out the leaving group. So what mechanism did we just do here? SN2, because it was the nucleophile attacks as the leaving group leaves. So that is an SN2 reaction. So what do you think happens next? Yeah. Perfect. That bromine, that bromide, is going to attack that carbon, because just like before, even though it looks weird, that is a leaving group. It looks like that oxonium ion, right? It's the oxygen with a positive charge. That is a leaving group. So we're going to have the bromide attack the carbon and kick out the leaving group. So the driving force here is not that we're going to make gases. What we're actually going to make is the phosphorus acid. So unlike the lithium aluminum hydride or sodium borohydride, where I told you like, okay, they technically are, they have more hydrogens. They technically can do the additional equivalence of hydrogen, but every time you make that bond, it gets weaker. The difference here is this phosphorus is really oxophilic. It loves oxygen. Phosphorus and sulfur are both oxophilic. They love oxygen. They make really strong bonds to oxygen. So this actually is 3 equivalents, I guess this one, is 3 equivalents of bromine. So it will keep reacting. So it'll do this 2 more times until you get to that. This thing has a really high boiling point, and so that's what's going to help it be easily separated. But this is going to be really stable. So this is the byproduct that's the driving force. It really does react 3 times. So you really only need 1/3 of this to every one of these, because you'll get 3 bromines from it. Or you could think of it as, if you were to put like coefficients somewhere, like you'd be like, that's a 3 and that's a 3 for every one of those. Right. Cool. Any questions about the phosphorus halide or the thionyl chloride? Sweet. Just another reagent to use that is going to force SN2 so it avoids any carbocation rearrangement problems. So again, this also has to be primary. It must be primary or secondary. Because it is also going to be an SN2 reaction. It'll only happen via SN2. Actually, I don't care about that. That step has to be via SN2. So that's why you need the appropriate alcohol, the primary or secondary alcohol. Okay. Any questions about that? Yes? So why does, say that again? Yes, sulfur can violate the octet rule. It's in period 3, so yeah. So why does this happen? So the reason that this happens, you're right, this is going to be really unstable, but the ultimate, we will make something that's a little unstable to have the big payoff of having the gases form. So it's one of those, like, this can go backwards. Like, all of these are technically in elimination, or in equilibrium until you get the gases. So it will, like, it'll make it, it can go back, it can make it, it can go back, and then as soon as it makes it, it's like running. Like, we're off and running as soon as you get those gases bubbling out. It is just ripping it forward. So you're right, this is not stable. Like, your chemical intuition looking at that, being like, that thing is weird looking. Yes, good. This is not something you would normally draw, except it helps you get to ultimately more stable products. It's almost like kind of like a necessary evil. It's a, necessary step along the way to have a big payout. Okay. All right, so let's actually talk about our ethers now. So our ethers are the, sorry, I meant to fix that. It's where you see that general ROR, the left and the right side don't have to be symmetrical. That oxygen atom is sp3 hybridized. I know it's sp3 because there's no resonance. So anytime you see the lone pair, you always stop and look and be like, ooh, is there resonance? If there's sp2 or sp next door, then you could have resonance. But because this is sp3 next door, it tells me that my oxygen is also sp3, right? So that's how I know for sure, even though it has lone pairs of electrons, it is that oxygen atom is truly sp3 hybridized. So that oxygen atom is going to be nucleophilic. It will also be a Lewis, or is the Lewis base. It'll be a weak base, but it is considered a good nucleophile. It is a good Lewis base. Our carbon atom that is next door is going to be slightly electrophilic because you do have those dipoles. Oops. So it will be that delta positive. So the carbon next door, immediately next to that oxygen, will be slightly electrophilic. They usually are used as a solvent, most commonly, because they have really low boiling points. So they only have those dipole-dipole interactions. There's no hydrogen bonding. So it's going to have weaker intermolecular forces. So it's going to have a lower boiling point. The reason that they're really good as solvents is that they are aprotic, right? There's no acidic hydrogen on them. So they're good aprotic solvents, really helpful for SN2 or E2. And they're fairly unreactive to most of our dilute acids and bases. We'll need concentrated strong acid or base in order to make them do anything. They're fairly unreactive to most oxidizing reducing agents. Most compounds are going to be soluble in them because they have both the polar and nonpolar sections. So they're pretty good at dissolving a lot of things. And they're easy to remove afterwards due to the low boiling points. They usually just evaporate when they sit there. They can just, like, in a couple minutes be gone. And we said the oxygens are good Lewis bases. This is going to help stabilize certain complexes. So it's going to help stabilize, like, our Grignards or the lithium aluminum hydride or the organolithium. Like, the reason that those are run in ethereal solvents, run in thiethyl ether or THF, is because they're going to help stabilize it. So that lithium aluminum hydride, our Grignard RMGX, and our organolithium, the RLI or LIR. So it's a good Lewis base, meaning it'll just help, just give a little bit of electron density to the metal to help stabilize the metal, but it's not a strong bond. Like, it's not a real bond. It's just kind of like, here, take a little bit of electron density. Oh, you want to react with something else? Cool, I'll go see myself out. Things to be aware of. Ethers, even though they are really good solvents, so they are used a lot in a lot of different settings, both like industrial and then also like at home, you might be using some ethereal solvents already. And just to say or write the word that I'm saying. So ethereal just means ether containing. So ethereal solvent is a solvent that contains an ether. So they are very flammable. So because of the fact that they have the really low boiling point, they readily go into the gas phase. So they go into the gas phase and they're going to have really low auto-ignition points, meaning they catch fire so easily. So the only lab fire I've ever started was I was trying to recrystallize a compound. And so I had it in diethyl ether, and I was adding too much diethyl ether. I was getting impatient, so I was trying to get the diethyl ether to go away a little bit faster. And so I was like, all right, I'm just going to turn the heat up a little bit. So for context, diethyl ether, its boiling point is 35 degrees Celsius, which is 95 degrees Fahrenheit. So it's not that hot. Like bath water, like the normal people like to take baths around like 102, 103 degrees Celsius, Fahrenheit. Celsius should be boiling, like that's boiling water. 100 is boiling in Celsius, but normally like 100 to 102, 103, that's normally where you would like have the temperature that you would take a bath in. 104 usually is getting a little toasty. That would be like hot tub level. Or actually that's what I like is 104 degree Fahrenheit, which is weird that I know that, but I have one of those IR temperature thermometers and they're fun to play with. So I just check temperatures of everything and I just like run around my house. Anyway, we're getting off topic. So anyway, So I had a reaction that had diethyl ether in it, and I was trying to get rid of the excess diethyl ether because I added too much. And I turned it up just a little bit, not that much. Like I just went from like a 2 to a 3 on the hot plate. And this sucker went and just was burning like flames. And I, very stupidly, don't do this. I panicked and grabbed it. Good news is it wasn't that hot because the boiling point's really low. So I was able to touch it and not have it actually be hot. So I was fine. Don't ever do that. That was so stupid because hot glass looks like cold glass. So it could have easily been like the temperature of the sun and I would have not known until I touched it. So don't just grab glass trusting it'll be cold. Like I got very lucky that I didn't have really severe burns. But yeah, so I just grabbed it off the hot plate, put it on the side, put a little watch glass on it to suffocate the fire. It went out, it was okay. But that's the thing, is like it catches so easily that you just need a little bit more heat and it goes up in flames. My also second favorite diethyl ether fire story is when I was a lab TA, one of my students, I'm helping, okay, so I have like student A, I'm helping answer a post-lab question. So we're talking. Student B comes up and is like, excuse me, Jen? And I'm like, yeah, hang on, let me just finish answering this question, I'll get right with you. And they were like, okay, all right. And I'm like, okay, so we're talking, all right, so this is what you want to do on your next post-lab, make sure you don't make the same mistake, you're great, good job. What's up? And I turn back to student B, and student B goes, yeah, the hood's on fire. And I was like, you need way more severity. Do not let me like ask you to wait. If there is a fire, you are the most important person. Like you get to jump line immediately. So whenever you're in any lab or life, like if you're like, there's a fire there, don't be like, excuse me? No, that's the time to be assertive and be like, no, we need attention because that's a problem. So yeah, so I go over and what it was they were quenching a reaction. They actually were doing a Grignard reaction. They were quenching their Grignard by adding strong acid. And they added the acid very quickly. And that whenever you run an acid-base reaction where you have a strong acid with a strong base, that's exothermic. It gets hot. It got hot enough that it caught the diethyl ether on fire. So then their reaction vessel was on fire. Fortunately, they were tiny vessels, so it went out very quickly because they ran out of solvent. But yeah, that's my other lesson of if there's a fire, you are the most important person in the room. Like, tell your TA, don't wait. But yeah, diethyl ether, super flammable, so easy for it to catch fire. In undergrad labs, graduate labs, no one is above a diethyl ether fire. So the other place I will put out the warning is that this is also a common solvent that is used as like a paint thinner. So if you do any sort of like oil paintings, it'll frequently be in either like the thinning agent or sometimes it's in the paints itself. So you want to make sure that you don't burn candles while you are painting because then you might actually light your apartment on fire. So be careful, like just be smart that it is making a flammable thing. Also, diethyl ether used to be used as the anesthetic? No, that's disinfectant. What's the thing where it knocks people out? Anesthesia. So it used to be used for anesthesia. So like the trope that's used in movies where they have carbon tetrachloride, where it's like you put carbon, what am I saying? Chloroform, that one. So, which actually is carbon tetrachloride, but anyway, chloroform, as we know it, is like they, have a rag soaked in it, and then they do that, and the person passes out. Although that was ancient days used to actually knock people out, the preferred method was actually to use diethyl ether. So diethyl ether is actually what most medical professionals was using, and that's because it was so volatile. So they would hold it over the patient's face, and they would breathe in the diethyl ether. And like we said, it's generally unreactive, so it didn't cause a lot of harm. But what it did do is it would displace all of the oxygen in your lungs. So then you would pass out. So then you'd be unconscious, so then you could have your surgery. So not great. We've improved a lot. A lot. But what I'm trying to get at is with diethyl ether, especially when you're doing any sort of, like if you're painting, or I found a bottle of solvent that my dad had in his garage that was like this rusty can, and I was like, we got to have another conversation. But those gases, that like the reason that like people can get high from them is because you are depriving yourself of oxygen. So you are suffocating yourself, and then it is displacing all the oxygen. So you actually start to have some brain damage and some cellular death because you are stopping your body from getting the oxygen it needs. Which, good news is your body is really good at self-preservation. So normally when you're passing out, that's your body's way of doing like, hey, have you tried turning off and on again? It is doing a hard reset on your life to be like, you aren't good at taking care of me. I will take over. And so it knocks you out so that then you're horizontal. So now it can ensure you have proper blood flow. It ensures you're breathing properly. And then it makes sure that you get all the oxygen you need to your brain again. So that's a good thing about the body. But also, yeah, don't huff things because you are causing cellular death. You are, like, if you're breathing it in, you're killing your brain cells. So don't do that. But that's also why it tells you when it says, like, work in a well-ventilated area. It's serious. Like, you want to have enough oxygen so that when your diethyl ether or whatever your solvent is becoming a gas, that it doesn't displace the oxygen that's going into your lungs. Like, if you can smell it, it's in your body. Like, that means you are perceiving it. So anything you can smell, you have taken into your body and is now interacting with your insides. So yeah, always make sure you're in a well-ventilated area. My other safety thing about ethers, the reason that I was very, very concerned about my father having that rusty old can of his paint thinner in the garage is ethers themselves are fine. But when exposed to oxygen and light, you know, the things that we have in life, so like sunlight and oxygen in the air, they will make peroxides. Remember that your peroxides are the ROOR. These things can be explosive. And so the problem with it is that they are both shock and thermal sensitive, meaning that if you ever find, if you have any sort of ether solvent and you find crystals on the cap, do not touch it. The simple act of trying to turn the cap to open it is enough of a shock sensitive that it can actually cause it to explode, and people have lost fingers from it. So like it will blow off your hand. Like don't do it. So genuinely, if you see any sort of crystals forming around those caps, the proper mode of action is to call the bomb squad. And the bomb squad, the local bomb squad should come in and actually dispose of it properly. So luckily for my dad, most commercial reagents are sold with a stabilizer because this is a known thing. They know this happens. So it's usually sold with a stabilizer to prevent the radicals from reacting, to prevent any sort of peroxides from forming. And so then it's meant to help you, not blow your hands off. That being said, stabilizers also break down over time. So they're really only good for like usually a year. And then if you've had something open that contains an ether, even with a stabilizer for over a year, you really should be checking it. And to be honest, you really shouldn't be keeping anything for that long. So my recommendation to students is always like, if you are a really avid painter, usually paint is the big one that's where you're getting it. But like, even if you're doing like woodworking, that also is really commonplace if you're doing a lot of woodworking. Check the bottle. You will see if it says that it'll say some sort of ether solvent. Look to then see, does it have some other reagent? You usually say some word or abbreviation, some sort of like proprietary code that means nothing. But then in parentheses, it'll say stabilizer. That tells you, okay, cool, this is gonna be safe for a little bit longer, because usually it takes 3 months for these to form. So it tells you have a little bit longer than 3 months, but you still don't wanna keep it more than like a year. You wanna actually properly dispose of it or use it readily. Okay, these are my life lessons for everyone, because they are common, they are everywhere. You will likely interact with these reagents even outside of a normal lab setting. So our common ethers are like diethyl ether, which always bothers me that diethyl ether usually gets abbreviated just to ether because it's so commonly used as a solvent. People just shorten the word. But ether, we know, is a functional group. So to be a little more precise, we're going to say it's diethyl ether. We also have furan, which is this 5-membered ring. Tetrahydrofuran is the 5-membered ring without the double bonds. pyran, tetrahydropyran, and 1,4-dioxane. All of these are very common solvents that are used. So the ones that we have seen already are the diethyl ether and the THF. We saw those with the lithium aluminum hydride, the Grignard, and the organolithium. That's where we saw those being used. So they're just more aprotic solvents. Other options, and you can use these if you like these. You can use these for SN2 or E2 if you're trying to get a good solvent for those. Crown ethers are only included because I think they're kind of cool. So I'm not going to ask you an exam question about this because, to be honest, I don't even know how I would ask you an exam question about this. I'm not going to make you draw a crown ether. But the really cool thing about them is they're essentially these molecular cages. So they're going to create a bubble, a trap of a metal ion, and they are size selective. So they can bind with very specific metal cations. So the benefit is it's actually used therapeutically where you can administer someone can take a crown ether, and it can help with heavy metal poisoning. So that it can actually trap out a heavy metal, and then now it can encapsulate it so that it doesn't react with you. It's now trapped and safe, and then your body can process it. So that's a really nice thing about crown ethers is they're really size selective. So you can say, hey, go grab this metal, and it puts it right in there. So like it's really good for chelation therapy. Chelation meaning just that binding, where it's just saying the metal shows up right in the middle, and it forms this nice little cage where all the oxygens are like, I got you, and they just hang on. So I just think that crown ethers are really kind of interesting molecules because they're, I don't know, they're kind of weird. You got like this weird loop and it just holds onto a metal. All right, for ether reactions, we have acid catalyzed dehydration of alcohols. We know it's dehydration just because loss of water. Remember, dehydration just means loss of water. It's nothing fancy. So these are really useful if you're trying to make a symmetrical ether, meaning you want both sides to be the same. And that's usually using sulfuric acid, your strong acid, and you would just have your alcohol. So you would just have, you would protonate, you would make an oxonium ion, one of your alcohols then becomes a leaving group, the other one becomes the nucleophile, it attacks, and you just get your substitution reaction. It works for both SN2 and SN1. It's really good for symmetrical ethers. In chapter 12, we're going to talk about how we can make ethers by adding an alcohol to an alkene. And so that's really helpful, especially if you get a tertiary carbocation, that you can make ethers that way to get an unsymmetrical one. So that'll be one way that we get where the left and the right side aren't exactly the same. So that's not this upcoming exam, but the next exam where that'll be there. The common way that is frequently run is essentially, it's an SN2 reaction, but it gets a fancy name of the Williamson ether synthesis. So this is really good for asymmetric ethers, meaning that the left and the right side are different. What you're going to do is just generate an alkoxide first, make a good nucleophile, and then add a good electrophile in the second step. Add whatever alkyl halide you want in the second step. So you make your nucleophile first, and then your nucleophile is just going to do SN2 and kick out the leaving group, and now they can be two different R groups because they're from two different starting materials. So you just have your alkoxide and your alkyl halide or haloalkane, and that gives you your ether. So it's a fancy name for I did an SN2 reaction. It's just specifically to make an ether in the end. Our cyclic ethers are where we get this special reactivity. So we can make cyclic ethers via substitution reactions. And it can happen where you have this alkoxide comes in and can kick out the bromine. And so we can do this. This is intramolecular. Intra meaning within. So this is molecular. So we have our nucleophilic site and our electrophilic site within the same molecule. So we're going to have a reaction where it's going to attack itself. So I'm going to be able to just, if my right hand is my nucleophile and my left hand is the electrophile, it's going to happen really quickly because they're attached to the same molecule, right? As opposed to if my right hand is the nucleophile and your left hands are my electrophiles and I'm trying to come shake your hand, it's going to take longer for me to get to you. So intramolecular reactions are always really fast because they're already attached. It's easy for me to do this as opposed to like running at you and trying to find you, right? So these cyclic ethers are going to form really readily via that intramolecular reaction where you have a nucleophilic site and electrophilic site attached to the same molecule. So what you want to do is count how many atoms away they are to identify how many atoms are going to be in the ring. So when we look here, we see there's 1, 2, 3. So that makes that 3-membered ring. And we see that it is an SN2 reaction. They will frequently be SN2. It technically could be SN1, but it usually will be SN2, getting that inversion, because you're usually making the strong nucleophile first, so it's going to attack right away. The ones that you really need to watch out for are the 3, 5, and 6-membered rings. They will form extremely quickly. So if you see that your electrophilic site is 3, 5, or 6 atoms away from your nucleophile, you're going to make a ring. It will reach over and grab itself. That happens very, very quickly. That will happen. If you make a 5 or a 6, they will also then be stable. So the thing about the 3-membered ring, remember when we talked about our ring stabilities, I told you 3-membered rings are highly strained. They're not stable. So the epoxides, our 3-membered cyclic ether, that epoxide will readily form, but it'll also readily open up. So it happens quickly because the nucleophile and electrophile are attached to the same molecule, but given the opportunity, it will pop back open. So it'll happen fast, but it'll also pop open really equally fast. Our 5- and 6-membered rings are going to be more stable, which is why these are what you commonly see as the solvents, where those 5- and 6-membered rings as the solvents that we talked about. Any other larger size, or even the 4, are going to be way less stable. We're not going to make them. So won't do those. Too slow. But 3, 5, and 6, you betcha. You're definitely going to make those. Really, really watching out for the 5s and 6s because that makes stable products. All right, so let's talk about the reactions when we break them open. So we had said that O-, because it was a strong nucleophile, strong base, it was a poor leaving group. So we had to activate it first. And we did that by adding a strong acid. And I'm really sorry that these are like where our structures are getting extra bad. So we are protonating it first. And then we're going to have our nucleophile come in. And I don't know what's happening with that arrow. The nucleophile can then attack either the left or the right side, right? Because I can imagine this being that is my leaving group or that is my leaving group, right? So I could either have this as a leaving group or I could have that as a leaving group. So we get a regioselectivity concern of do you attack the left or the right side? And that'll determine what products you get is to which side you attack. So in this case, I attacked the right side. So I got the alcohol with the red carbon, and then the nucleophile was attached to the blue carbon. But it could have easily happened the other way. So to know which side you're going to attack, it depends on are you doing SN1 or SN2. So if you're doing SN2, we're going to prefer our primary or secondary side, whichever is acting like a primary or secondary leaving group. And it'll prefer a strong nucleophile. Oh, it's 10:05. All right, we'll finish this on Monday where we'll do our epoxide rings. Like, we are almost done. That's it. And then we'll do synthesis. Have a wonderful weekend.